In this topic, we'll focus on how digital signatures prove who created code or documents and that they haven't been altered. You'll see how Luna HSM managed keys perform signing and verification, and how these operations support secure, trust-based enterprise workflows. You've already seen how Luna HSMs are structured, how clients connect, and how keys are created and managed through APIs for encryption. Now we'll reuse those same building blocks for digital signatures and verification, setting you up for PKI, TLS, and full infrastructure integration. Digital signatures and encryption solve different problems. Encryption hides data, so only someone with the right key can read it. A digital signature doesn't hide anything. It proves who signed the data and that it hasn't changed. The signer's private key creates the signature, and anyone with the public key can verify it. When combined with trusted certificates, policies, and logs, signatures also support non-repudiation. Here's how a Luna HSM signing operation runs end-to-end. Your application authenticates to the correct partition, then sends either the data or a pre-computed digest through the Luna client library. Inside the HSM boundary, the signing key's attributes are checked, and the private key operation is performed entirely in hardware. Only the signature leaves the device, so the private key material is never exposed to the application or the network. Verification starts with 3 inputs: the original data, the signature, and the signer's public key, usually carried in an X509 certificate. We first recompute or receive the digest of the data. Then the cryptographic algorithm checks whether the signature matches that digest under the given public key. Next, the certificate chain is validated up to a trusted root. Only when all these checks succeed do we treat the signer's identity and the data's integrity as trustworthy. With PKCS number 11, every signing flow follows the same basic pattern. You already have a session handle, and you've located the private key, referenced only by its handle. Seen in it ties together the session, key handle, and mechanism, which defines the algorithm and digest behavior. You then stream data or a pre-computed digest with csign update. Finally, csign final, or the one-shot csign, returns the signature for that mechanism. Think of HSM signing as a stack of abstraction layers. At the bottom, PKCS number 11 gives you maximum control over mechanisms, sessions, and error handling, but also the most code to write. In the middle, OpenSSL engines and providers plug Luna into existing TLS and crypto flows. At the top, Java, JCA, JCE, C#, or vendor SDKs feel more familiar and concise. Whatever layer you choose, always confirm the key actually lives on the HSM, not in a local software store. Choosing a signing algorithm is about balancing modern security with real-world compatibility. RSA-PSS with SHA-256 or SHA-3884 is the preferred modern default when your ecosystem supports it. ECDSA with the same hashes offers high efficiency and is common in newer PKIs and constrained devices. Traditional RSA PKCS number 1 version 1.5 with SHA-256 is mainly for legacy systems or strict interoperability. In every case, align algorithm, key type, and hash with your certificate profile and verifier expectations. There are 2 signing modes to keep straight. In a combined mechanism, you hand the full message to the HSM, and it performs both hashing and signing with a known algorithm pair, such as SHA-256 with RSA. In a raw mechanism, your application hashes first, then sends a digest or encoded structure to be signed. If the mechanism doesn't match what you actually send, you either double hash or send a digest in the wrong format, and verification will fail. When you define a signing key in a Luna HSM, think in 4 dimensions. First, attributes. Mark the key as sign-only, not for decrypt or unwrap, and make it non-extractable and HSM generated. Second, access control. Map use of that key to specific roles, quorum rules, and client identities. Third, lifecycle. Govern who can rotate, clone, or destroy it. Finally, audit. Log every sensitive operation so you can later prove how the key was used. Code signing with a Luna HSM is all about tightly controlling access to the private key. The build pipeline sends an artifact, or just its hash, to a dedicated signing service. That service is the single gateway allowed to request signatures from the HSM. Inside the HSM, The protected code signing key and its certificate generate the signature. The signed artifact, along with its certificate and timestamp, is then published and later verified before install or at runtime. In a real enterprise pipeline, code signing should act like a gated service, not a background library call. Builds request signing from a dedicated service, approvals gate access to production keys, and each environment uses its own certificate. Every signature produces an auditable record that ties the artifact, signer, key, and time together. Document signing focuses on preserving trust from approval through long-term validation. A user or workflow first approves the final content. The document platform hashes that content and sends only the hash to the Luna HSM. The HSM signs with a protected private key tied to an X509 certificate. The platform then embeds the signature, certificate chain, and timestamps, so recipients can verify integrity now and auditors can still validate it years later. Digital signatures only work if verifiers trust the entire path behind them. The HSM protects the private key, but the certificate authority ties that key to a real identity or service. Verification environments then check the certificate chain and consult OCSP or CRLs to ensure it hasn't been revoked. Timestamping adds proof of when the signature was created, so it can remain valid even after the certificate expires or is revoked. Digital signatures prove who signed and that data hasn't changed, but they don't hide the content. Luna HSMs keep private keys inside a hardened boundary while your applications sign through PKCS number 11 or higher level APIs. Strong workflows, certificates, and timestamps make code and document signing trustworthy. From here, we extend this same trust model into TLS and enterprise PKI.